Okay, thank you all for coming. My name is Jim Laris. It's a great pleasure to welcome David Tarditi back to MSR. Those of you who don't know, before David went off to join Midori and run the compiler effort there, he was a researcher in MSR for many years. That was actually the genesis of this compiler, was a research project in MSR. And David will tell us about it. So, David.
Thanks, Jim. So I'm going to start. So as Jim mentioned, Bartok was originally a research compiler in MSR. It was used as part of Singularity. And today I'm going to tell you about some of the stuff that we've been doing since we took the compiler over to this Midori effort. And I'm going to give you an update on what we've been up to for the past couple of years. This talk's going to be a fairly high-level talk, so it's a 35,000-foot overview. So I'm going to be talking about Bartok, which is a compiler that underlies Midori. I'm going to ask that you guys hold detailed questions to the end of the talk. I've got a fair amount of material to go through. Clarifying questions, I'm happy to clarify as I go, but detailed discussions we should hold off to the end. And we'll schedule future talks based on interest. So depending on what people find interesting, there's a lot of topics in here. Many of the topics we could talk for a full hour on themselves. We'll schedule some future talks based on what people would like to hear about. So Midori is a new operating system, and the interesting thing about it is it's written, or one of the interesting things about it is that it's written entirely in C#. And there are things that go beyond just the C# stuff, lots of stuff that goes beyond that, but it's written almost entirely in C#, and the goal here is why do we use C#? Fundamental reasons are we want the developer productivity and the reliability features of C#. And the OS itself is written in almost entirely in type-safe C# code. The type safety forms the basis for concurrency safety and lightweight processes that we use in the operating system. So besides providing productivity benefits, we're relying heavily on the type safety benefits of C#. So today's talk, I'm going to focus on basically what do you need to do, what have we done to make sure that you can actually build an OS in C#. So the question is, what do you need to do to make change how you compile C# so you can use it to build an OS? So there's three approaches that we've taken to provide the foundation for Midori in terms of compiler support. The first thing we've done is we compile ahead of time. And I'll explain the reasons why we do that. But that's the basic idea is this is sort of more like the traditional C++ environment where your compiler takes the code and then produces a binary. The second thing we've done is we've done a bunch of work on reducing the time and memory overheads of managed code. So I'll go through at a high level 5 things that we've done here, all of which are important. There's actually more. We've actually done more. I just picked the top 5 for performance reasons, the top 5 that contribute to performance. The third thing is it's a highly optimizing compiler. So I'm going to go at a quick pace through some of the optimizations we do. But the important thing to understand is that usually when people look at a managed code OS, you're not comparing comparable compiler technology. So people say, oh, managed code is slow. Well, in our case, we've got the same optimization capabilities as production C++ compilers. And I think this gives us a significant advantage. We've actually taken the optimizations and in many cases extended them for managed code. So for example, we had to take PRE and make it more aware of exception handling and the implications of exception handling for code motion. So we've taken, we start with a highly optimizing compiler and we've extended it for managed code. So just a refresher, it's been a while since we had a Midori talk here. We have this nice brown bag series, but I think it was March when we gave the initial talk. This is an overview of the Midori OS. The important thing to understand about this is that, like I said, we rely on type safe from the compiler perspective. We rely on type safety to provide isolation between processes. So the system here, you'll see that most of the system is written in C#. It sits on top of a microkernel, and it really is a classic microkernel that's sort of just doling out some basic resources. It sits on top of a microkernel written in C++. There's the way things work in Midori, you have a set of domains. Each domain provides hardware isolation. So the idea of domains is that if you have code that truly shouldn't be trusted, for example, you have some game you downloaded from the internet, you shouldn't put it in the same domain as the thing that you're running your browser that has all your banking information in. So within a domain, there are software isolated processes. And the thing to understand is that this is the classic microkernel architecture. Everything runs in a process. The domain kernel is really in charge of resource management, both policy and mechanism. But all of the stuff, device drivers, user processes, resource management, application startup, UI, all of that runs at the user mode level in processes here. And for the purpose of this talk, the important thing to understand, we really are talking about the vast majority of the system being written in C# here. So just to refresh your memory about Midori and what it's capable of, this is a slide that I pulled from the March talk on Midori here. And the important thing to understand is that Midori can deliver performance that's competitive with Windows. So this particular slide shows the performance of SpecWeb, which is a well-known benchmark for web servers. And the blue column here is Windows. The green column here is Midori. And we've done the usual benchmarking things. We've tried to make this comparable in all cases. There's some things, it's the same stuff that you'd use to submit to spec.org if you wanted to. And what you'll see here is the higher number is better. So this is number of web connections that you can serve meeting a certain criteria of quality of service here. And so Midori achieves 78,000 connections. Windows achieves 49,000 connections or so. I'm not here to say like, oh, we're much better. I'm just saying we can deliver performance competitive with Windows with this system. So I want you to understand that's where our goal is to meet or beat performance of existing commercial systems. So ahead of time compilation. So for people who are familiar with the C++ world, the idea is that your world is going to look fairly similar to the way it does for C++. So here you have C# code. It gets translated by the C# compiler to MSIL. You have the Bartok compiler, which takes the MSIL and translates it to an object file. And then finally, you do linking, and you get an executable file here. The thing that makes this challenging is that C# has generics. So we actually, in this approach here, to achieve true ahead-of-time compilation, we have to instantiate all the generic types at compile time. It really wasn't clear when we first set out on this project whether that would work or not, whether you could get lots of generic types. For the core system, we've dropped the C# features that rely on a JIT. So what this means is that like when you're building the file system, we don't really need reflection, to be honest. Or when we're building the networking system, we don't really need dynamic class loading. So we dropped features that were in C# that rely on a JIT. So we have narrowed the set of things that you can write in the programming model. I don't think it's been a huge loss for people. And we still do use a JIT for dynamic scripting languages. So on this system, we support JavaScript in the browser. And frankly, to make JavaScript run efficiently, we rely on JIT compilation. But the core system is ahead of time compiled. So what are the advantages of ahead of time compilation? Why would you do this? Well, the first thing is you can get faster machine code. So you can avoid the constraints that come with a JIT of having to trade off runtime and memory footprint for optimization quality. The second thing, of course, is obviously you avoid the runtime system and memory footprint overheads of a JIT. And in our world, what we're trying to do is achieve small, lightweight processes for isolation purposes for things like error handling and recovery and resiliency. So we're talking about processes where we're trying to achieve 145, 100K overhead for starting a new process. It's important to avoid unnecessary costs there. And finally, it lets us reuse the existing OS approaches. So when we need to go figure out how to do crash dumps, or we need to go figure out how to do debugging, we can reuse the existing approaches that are already there. So for example, in crash dumps, we pretty much know the binaries that are deployed on the systems. The binaries were compiled in some build lab somewhere. So we can take a crash dump, and then you correlate the crash dump with the actual binary that you've got at hand. The disadvantages of this, well, I mean, the disadvantage is the obvious one, which is that JITs are great in terms of having a great rapid development experience. So the compile times for Bartok are definitely longer than what you see with a JIT. I don't think they're not so long as to be completely unreasonable, but it's definitely longer, and it's a longer development cycle. I mean, I think we're in between where you'd find C++ for Windows versus a JIT in terms of the development experience. Now, Windows always has optimizations turned on, so they're incurring a lot of cost there when they do compilation. So ahead of time compiled generic. So why is this hard? So in Bartok, we use a non-uniform representation for generic code. So what this means is that, like the CLR, we take the generic type, and when you instantiate the generic type, we specialize it to the particular type that you're instantiating. So in particular, if you have a value type in .NET and say it's 8 bytes or 12 bytes in size, we're going to create a specialized copy of the generic code for that value type. Now you might say, well, why would you do this? If you do ML, a lot of times ML has a uniform representation, for example. If you do camel, that kind of stuff. One of the key things is in systems programming, you really want to avoid unexpected heap allocation. So there are parts of Midori where you literally, for correctness, you can't do heap allocation at that point in the system when you're really far down in the guts. There are other parts where you want to avoid the unexpected boxing just for performance reasons. So allocation can be costly. You really want to make sure that you don't box things in some unexpected fashion. And my claim would be that it's actually sort of non-obvious to programmers when they're using generic code where you would get boxing, where you don't get boxing. So we've bitten the bullet, and we just go with the non-uniform representation strategy. The CLR handles this non-uniform representation strategy by using the JIT to instantiate types. So at the CLR level, when you only build the generic types that you actually need during the run of the program. So in the CLR, they lazily instantiate the code. And CLR has ahead of time compilation as well in the form of NGen. But NGen can always rely on a fallback. So they've always got a net behind them, which is, oh, we can just use the JIT if it gets too hard. In our world, what we want to do is instantiate all of the generic types at compile time. And to be frank, it wasn't really clear when we started how well this would work. You can get a large number of generics. And the way, when you instantiate all the generics, it does have a significant interaction with the way libraries work. And I'll talk about that later in the talk. So to give you an example here, this is an example of what can happen or how you can get lots of types created when you have a generic type. So in this case, this is code pulled from Midori. So this is pulled from the Midori hash map collection. This is mapping. You have some key. You're going to map some key to a value. So this code here is pulled from the actual implementation here. There's a comparer, which is an object that provides your hashing function. There's an array of entries that you have for the hash table. There's a count. And the way the implementation works, there's an integer array that they use for the bucket implementation. They sort of do a level of indirection using the buckets here. So what happens here, though, so if you look at this here, when you take hash map string of int, you end up with a whole bunch of types being created. You end up with map of string of int. So you have the superclass that you have to create. You have map entry string of int. This is the entry in the buckets here. So this is a struct type here. You have a hashing comparer string, which is used here. You have an empty array, which is a specialized version of array, which has map entry of string of int. So it's instantiated to map entry string of int. So we get 5 types. There's actually more types created. I just showed you the snippet of types that are created for this subset of the code here. So we end up with 5 types. And then you look at map of entry to explain the specialization here. The map of entry here will get specialized. We'll have a map of entry instantiation here. Be 20 bytes on x64. So hash code is an integer. Next entry is a pointer to the next thing. Here we have key, and we have value. And then if you look here, map entry string of string, then here we have something that's going to be 24 bytes in size. And so the key point is we actually have to generate distinct types for things as we do ahead of time compilation. And the question that was sort of underneath it all was, well, how well is this going to work in practice? So I'm going to talk a bit about our strategy for implementing generics, and then I'll actually give you the high-level summary of how things actually worked out. So the first thing we have to do in our approach is we have to prove that the number of generic instantiations is finite. So in our approach, we actually have an algorithm. It's based on an algorithm the CLR used. We extended it a bit. And it's a conservative approximation that says, yes, you can unfold or instantiate all of these types at compile time. Basically, you build a graph of classes, and you have a node or arcs between classes when an expansion occurs. And you basically look to see if there's an infinite expansion possible in the graph. It is a conservative approximation. So there are some cases where we will reject a program because our algorithm can't prove that the expansion is finite, even though the expansion is actually finite. The second thing is that each generic instantiation gets its own v-table. So this directly interacts with what I talked about with the concern about how many types get created. So the v-tables, just to be frank, they can be costly. So I think they rival machine code in size in an executable. C# has runtime type identity. If we want to keep the C# semantics, we have to have v-tables or some way of establishing runtime type identity. So I think code is about 50% of the size of an executable, and about 30% of the size of an executable is probably v-tables. We have, and this was a surprise to us. We didn't expect this when we started. We actually optimize v-tables, so we can prove that runtime type identity doesn't matter and the v-tables are structurally identical. We'll fold them together. The third thing we do is we do implement generic sharing, just as the CLR does. So like the CLR, Bartok uses type passing and dictionaries to implement sharing. So in particular, if we have runtime operations that are dependent on the type, so you have some generic type, it's been parameterized by some type variable, you pass in an extra argument, which is the dictionary, which says basically how do you actually implement that operation. So for example, what's the type identity at runtime of the type variable? The sharing decision is made on a per method basis in our world. An example of that is constrained virtual calls. You could, in theory, share them with a lot of work, but in fact, for constrained virtual calls, the programmer expects a certain behavior, which is a direct call. So we, for methods with constrained virtual calls, we won't share them, for example. One thing that we do that's different than what the CLR does is we actually do sharing over value types. So the CLR just does sharing over reference type arguments. The reason for this is that what we found is that systems programmers like to use value types. And they like to use value types because they don't have heap allocation associated with them. So when we see code in Midori that's actually quite different than what you might see on the CLR. So we actually see a lot of generic instantiations with value types involved. So I'm going to give you the 35,000-foot overview of the empirical evaluation of generics. The question is, are we going to end up with lots of code, or are we going to end up with a reasonable amount of code? So in this case, what we've done here is this is a comparison of the incoming MSIL and the size of the resulting native images on Midori. And this is for a standard Midori build. And so the idea here is that the MSIL itself has one copy of generic types, and the native code has multiple instantiated copies of generic types. And so if we had some problem with sort of runaway expansion of generic types, you would expect that there would be a big increase in the size of the code with the instantiations in it. MSIL is a bytecode format, so MSIL is very compact. You'd expect a small constant factor expansion for code. If you look at just non-generic code, you get a small constant factor expansion. So the ratio that we saw here is we see roughly a 3-to-1 and a 2, or anywhere between a 2-to-1 and a 3-to-1 expansion over MSIL. So the entire Midori system, clocks in at about 198 megabytes of code. So I'd say from our perspective, this has been successful. We can instantiate generic types at compile time and get reasonable code size. You might say, well, are generics used? I mean, maybe people just don't use generics. And I have a lot more numbers behind this for the sake of brevity. I'm not going to go into them. But the generic methods themselves are about 30% of native code size. So there is a lot of use of generics in Midori. And we are able, even though they're widely used in the code, and programmers don't really think twice about using generics, we're still able to achieve a relatively good code size ratio. So I'm going to switch gears. I've talked about why we want to compile ahead of time. And now I'm going to talk about 5 features that we implemented to reduce the time and memory overhead of managed code. I actually already covered the first feature, which is generic sharing. So I'm going to talk about the next 4. And I'm only going to spend a few minutes on each one of these. I will come back and discuss the implementation of shared libraries in depth. So the first thing that we did to make the code more efficient is introduce shared libraries. So the gist of the story is that programmers who are using a language like C# expect to have a rich set of class libraries at their disposal. We're aiming for a world where we have lots of lightweight, small processes. So for example, the Midori new process memory footprint. So this is the additional memory required when you start a new process. It's 145K of memory. The solution which we adopted is an old solution, which is that you introduce this notion of shared code. So you create libraries and you share them across many processes. So on both Windows and Unix, they have this notion of shared libraries. The idea is the code is loaded only once, if you're lucky, and then you can amortize the memory footprint of the code across many processes. To provide, the thing that's different about us is we want to provide the rich object-oriented experience. So in our world, what we decided to do is allow any object-oriented type to be exported from a library. This includes generics, which complicate your implementation. In contrast, Windows exports flat interfaces. What this means is that our trade-off is that when you change a library, it may be a breaking change at the binary level. So you change a library, you may have to recompile an application that depends on the library. 15 years ago, people would have said, wow, this is completely unreasonable. You can't possibly do this. We need binary compatibility for libraries so we can update them. So if there's some kind of bug and security bug, we can patch the library and not have to rebuild the application. We don't know where our library goes to. Fortunately, times have changed. And so we now have app stores. So we understand who is actually consuming our library. And we can recompile the apps if the library changes in some kind of breaking fashion. I won't claim that this is the final story, that this is a great thing. It's still playing out to see how well this works. But my point is that this is a reasonable thing to consider given the advent of app stores and the advent of machines that are connected. If you can update the libraries, you can also update the apps. So to give you an example, I went and looked at the actual shared libraries we've got in Midori today. We actually have 21 shared libraries. I'm not going to go through all of them, but these are some examples of the libraries that we have. And I picked, obviously, some of the more important libraries. Platform Core is our equivalent of MS Corelib. So it's got the core functionality of the system: collections, concurrency, cryptography, strings, the runtime system, the garbage collector, that sort of thing. And the incoming MSIL size for Platform Core is about 8.5 megabytes of MSIL. If you guys have done C# programming and looked at the size of MSIL, that's a lot of code. The native size is about 11 megabytes of code. So again, this gets back to my point about, how do you achieve giving somebody such a rich library and keep the process size small? So platform graphics is the graphics stack. That clocks in about 4 megabytes. Platform runtime here is HTML rendering. It clocks in about 8 megabytes. So we really are trying to achieve small, lightweight processes, but give people the rich set of libraries that they're used to programming for an object-oriented system like C#. So as I mentioned, the compilation model is such that application compilation is brittle with respect to libraries. So that if you change a library that another application or library uses, you may have to recompile that other application or library. And there's 2 sort of primary causes of this brittleness. The first one is generics. So like I mentioned, we specialize generics for a non-uniform representation. So you may see a generic type instantiated at a type that you've never seen before, or particularly a size of a type that you've never seen before. And the second is what people call the brittle base class problem. So in the brittle base class problem, you change the layout of a base class in the library. That means that the offsets for the layout of a subclass in an application have to change. I'll note that this kind of, the brittleness here cuts both ways, though. It means that we can use information about libraries during optimization. So in particular, we can do cross-compilation unit inlining of method bodies, which is important for performance. And we can also see, hey, did you already instantiate this generic method, and can we reuse that? So we have a compilation model that is different than what you see elsewhere with respect to libraries. But it's, it has some disadvantages, and it also has some advantages from a performance perspective. I will talk more about how that's implemented in a few minutes. I'm going to switch gears and talk a bit about class initialization at process startup. So in C#, there's a there's a class constructor semantics that for ahead-of-time compilation will lead to runtime checks. So in particular, C# either has lazy class initialization, which is similar to Java class initialization in that you initialize the class only when you're really certain that you need it. It also has what they call before field init semantics, which is a looser form of class initialization. And with before field init semantics, you have to initialize the class sometime before you use static fields. In both cases, this leads in ahead-of-time compilation to you needing to introduce explicit checks before field accesses, either semantics. If you use C++, you don't get runtime checks before you go to use a static field. You just get to use the static field. So this is a sort of peanut butter cost that you would pay if you just took the classic virtual machine approach, runtime virtual machine approach to implementing class constructor. This is just something that you would pay if you're just trying to implement these semantics that you wouldn't pay for C++. And if percent here or percent there, soon it starts to add up to real performance. So to avoid these checks, what we've done in Midori is we've just sort of dropped that class constructor semantics model. So we've replaced it with the idea that all class constructors will be run at process startup. So what we actually do is we actually have a compiler analysis that decides on class initialization order. If you're familiar with .NET, you'd say, whoa, wait a minute, you're going to run class constructors at process startup? Class constructors can do I/O on .NET. You can print stuff out. Well, in our world, Midori is a capability-based system, and class constructors get no capabilities. So class constructors can't do I/O in our world. So we don't have to worry about a class constructor trying to do a system call while we're starting the system. So what we do is we build a dependency graph for class constructor code. So we actually analyze what class constructors have to be run before others. We do a topological sort. And again, this is something where we've changed what happens. If we find a cycle, so you define a class constructor A that mutually depends on class constructor B, so A and B reference each other, something you shouldn't do, but it does happen in .NET. You really shouldn't do it because the semantics are very subtle. We'll reject the compilation unit. So we'll simply say, sorry, you've got cycles in your class constructors. That's not permitted here. One thing we do here, the question that comes up is, so when you use a class constructor, you can do things like do virtual calls. You can call into a prior compilation unit. You can pass your objects off to somebody else. We just make worst-case assumptions when that happens. So if in your class constructor you do virtual calls, we're just going to assume that that code is called right there and then at that point, and that those static fields that call depends on have to be initialized. It was actually an interesting thing. We weren't sure how well this would work out. So just making this conservative assumption actually works reasonably well in practice. I think part of that is tied into the fact that we've limited what you can do in your class constructors. So you can build data structures. You can't do I/O. So to provide you, this is an example of how the class construction works when it interacts with libraries. So we compile library 1. We come up with an ordered list of static constructors. Then we compile the libraries that depend on library 1. We compile library 2. We compute the schedule there incrementally. So we assume that all the static constructors for L1 have already been run. So we know L1 is taken care of. We create a list for L2 here. We propagate the lists up to executables. And we merge them, and we create a list of, this is the list in which you should initialize your class constructors. Our libraries are DAGs, so the dependencies for our libraries are DAGs. So in particular, we can't end up with cycles here in our approach. And the key thing is making the conservative assumption about what happens when you pass code off to a prior library. Now you might tell me, well, but Dave, we're gonna now initialize all class constructors at process startup. This is going to be expensive. I mean, you could have thousands of class constructors to run through. This is going to affect your process startup time. So we have another feature that we added, which we call frozen objects. And the idea of this feature is to have statically initialized data at compile time. So if you're familiar with C++ programming, you have initialized data. So we've taken this one step further. You can sort of specify initialized data in a limited fashion in C++ programs. And what we try to do is we actually try to evaluate every class constructor at compile time. And it helps that .NET has nice semantics for MSIL. It means we know what the meaning of the program is supposed to be. So we actually try to evaluate the class constructor ahead of time. The advantage of this, well, the first one is this is a good way to solve process startup times or improve them. We avoid the cost of running class constructors. We get to reduce memory footprint. So in particular, if you have some class constructor, we can evaluate it at compile time once for a library and then share the results across every process in the system. And of course, it's GC friendly. This is read-only data, so the GC doesn't actually need to do anything here. There's no scanning that happens. We treat this as an optimization. So we don't guarantee that we're going to initialize all class constructors at compile time. So when we do this, what we can do is we try to symbolically evaluate the code. And if it doesn't work, we just say, oh, we're going to defer initialization to process startup. We actually give you a message that says, by the way, we weren't able to freeze this type. The optimization that we do depends crucially on Midori's TSE type system. So here what we're doing is we're taking a graph of objects and putting it into read-only memory. The classic problem that you'll run into on .NET is, well, somebody could try to modify that graph of objects after you've initialized it. In our world, what we do is the programmer can specify immutability, deep immutability of object graphs and fields. So we're able to rely on a TSE, the TSE type system for Midori to be able to pull this off. So in terms of how things work, like I said, this is really just it's just an interpreter at compile time. We actually embedded the interpreter in the middle of the compiler, so we actually do it on Bartok IR. We're lucky that MSIL has this nice semantics. We actually support pretty much everything almost everything that you can do in MSIL. So if you have native code calls, so for example, somebody's implemented an intrinsic in native code, we can't freeze that. We chose not to freeze code that throws exceptions. And there's some unsafe code operations that aren't supported. So if you do unsafe arithmetic and you go beyond the bounds of an object, we're going to tell you, sorry, we don't really know what you're doing at this point. You're trying to access random memory, and we don't model that. The tricky part in terms of implementing this for the compiler was that we now have to load the code from libraries that are used in class constructors. So we actually have to reach into the libraries and load the code in the compiler. We did struggle with keeping compile time under control. What we ultimately decided to do was load only the types that are reachable from class constructors. Fortunately, this is a small fraction of the types that are available in the system, so it's like about 10%. And in the long run, if the system got larger, we'd probably restrict the set of types or set of classes that you could use in class constructors. The system gets very large. So the end result is that in our system, I believe we're able to freeze about 90% of class constructors at compile time. A lot of class constructors are doing things like, if you look at something that might be initializing the empty map, for example, that I referred to earlier. So a lot of the class construction operations aren't really complicated. The advantage of this approach, though, is you have the full power of your programming language available when you're doing your static initialization. So what this means is that you can build complicated object graphs in memory, and they'll be frozen, and it's done with at compile time. So for example, if you need to build some kind of special map for your system, or you want to build Unicode tables or whatever, you're not constrained to fit them into arrays. You can build sort of whatever data structure you feel is appropriate. Of course, you have to build a data structure that isn't too big. It has to be something that you actually want to have in physical memory. And your compiler will take longer to run if you give it a very long or complicated computation. Another thing we've looked at in terms of making managed code more efficient for Midori is what we call efficient linked stacks. So Midori has an asynchronous programming model. And basically, when you go to do a system call, you tell Midori, I'm doing the system call. When you finally finish with the system call, come back and execute this code. This is similar to the async model that exists in .NET now. So this approach here, what happens is computationally, you end up building up a long list of work that's pending to be done. And the problem that you run into when you do this is, you've now suspended some computation. You're waiting for the result to come back. If you use large stacks, say the Windows approach where you take 64K of actual physical memory, or reserve actually, take 64K of memory, and then you have, say, 1 megabyte of virtual memory reserved, this does not scale. Midori has thousands and thousands of these suspended computations existing at once. There was a paper in SOSP 2003 which described a solution to this, which is the notion of using linked stacks. And it was precisely aimed at this kind of problem with concurrency. So the idea is that you take your stack, instead of having one contiguous stack, you break your stack into segments, and you add a new segment when you need more space on the stack. So in this way, the stack usage can be proportional to the amount of stack space that the program actually needs. And this is a good thing, except for the fact that there's more peanut butter costs coming with this. Now, when you enter a function, you need an explicit stack check. And you might need to link a new stack segment. And what we found in our experience, this is costing us 2 to 5% of performance. It depends on the program and what you're doing and the kind of recursion and that kind of stuff. But it was significant cost. And like I said, a few percent here, a few percent there. Soon you're talking about real performance. So what we've done in Midori is to take advantage of an asymmetry between async code and synchronous code. So at the type system level, we differentiate between the two kinds of methods, synchronous and asynchronous. So in the type system, when you have asynchronous code that's going to block, it's reflected in the signature of the method. When you have synchronous code, it's also reflected that it doesn't have the async type in front of it. What it means is it can never block. So it can't suspend itself. It can't do a system call. It's basically computation. So what we do is we execute the async methods on linked stacks. And then you have this transition where you can go from async to sync, but you can't go from sync to async. For synchronous methods, we switch to a large stack using a guard page. And this is all declared in the type system. So we don't need to put in explicit stack checks for synchronous code, nor do we have to worry about needing to link and unlink stacks in that area or in that piece of code. The thing to understand here is this is more of a co-routing model, which is that once your synchronous code starts to run, you're not going to yield the process until the synchronous code finishes. So we're not in the classic world where you have tons of threads and, oh, you've suspended a thread and now you need to take the large stack. In this case, basically, a Midori process has one thing happening at a time, and the synchronous method will run to the end. So we actually did extensive optimization of linked stacks to make them efficient for Midori. So the first thing we did was we optimized the switching between stacks. So this is actually an interesting piece of work. We treat the stack switch, we cast it as a registry allocation problem. So we actually have the stack switching done and the decision about where to place the stack switch done by the allocator. So the classic case is you have async code, and it's got a large blob of synchronous code within it. So if you switch back and forth on the stack every time that you did a call, this would be wildly inefficient. So you called F, G, H, and you switched every time. That would be very inefficient. What we can do is treat the stack pointer as an implicit argument to the call. And it's an implicit argument that just like the register allocator just sees this as, oh, this is a register that needs to be reloaded. And it has one of two possible values. The register allocator is already in the business of minimizing loads of values into registers. So we let the register allocator place the stack switch. And it naturally pushes the stack switch, for example, out of hot loops. It pushes the stack switch out of code that looks like it's costly. And we have a hierarchical-based register allocator. So we end up with minimizing the dynamic cost of stack switching here, at least based on the register allocator's model. And we make sure that important runtime methods are stack neutral. So there's a bunch of methods where, if you call the type test stuff, if you call for a runtime type test, you don't actually need to switch stacks. It doesn't use very much stack, so you're good to go on that. The second thing we did was we modified the calling convention. So in our world, stack space availability is part of the calling convention. So we guarantee that there's a certain minimal amount of space available, and I think it's 128 bytes or 256 bytes, when you enter a function. What this means is that when you call into, for example, small leaf functions, you don't actually need to have a stack check, and you don't need to worry about incurring the cost of stack switching. We basically just optimize the calling convention for small functions, which sort of, because they're small, they tend to use a small amount of stack space. The third thing we did was minimize the cost of stack checking. And so in this case, what we actually do is we actually try to push the checks up the call graph. So we have an interprocedural analysis that calculates the max stack required. When the max stack required gets to be too big, it's going to exceed what would be available in a segment. Then we cut off, and we just insert a stack check at that point. In our world, because we can make assumptions about the libraries, we can propagate the requirements across libraries. So in this way, we're able to, even for asynchronous code, minimize or reduce the overhead of using linked stacks. So now I'm going to switch gears a bit. I went through 5 features: generic sharing, libraries, the class initialization, frozen objects, and efficient linked stacks. And we actually have more stuff we've done, but these are the sort of top 5 I'd rank in terms of performance impact. And I'm going to discuss how we implemented the shared libraries in depth. So in our world, a library is a set of MSIL assemblies that are all compiled into the one native image. So as you saw, the MSIL was pretty big for platform core. It was over 8 megabytes. You really don't want to be compiling that amount of C# code in one go. So in our world, we actually take a set of MSIL assemblies and compile them to one native image. Now, the library actually has to provide certain things as part of this at runtime. So the library defines the code for methods, static fields, the read-only data that I talked about for frozen objects, as well as other forms of read-only data like strings, and runtime metadata for types like vtables. So we actually have to provide some way at runtime of accessing all of these things. So Midori itself, remember I mentioned the processes are implemented in software. So the processes actually all run in the same address space, and we need to figure out a per process way of having an instance of a field. So every process has to get its own copy of the static field. So what we actually did is, and normally on Windows or on Unix, you'd play virtual memory tricks to do this. We had to just bite the bullet and implement this in software. And we use something we call a CPU environment block. So for people who are familiar with Windows, this is analogous to TLS, thread local storage. We actually have per process storage. So this is more like process storage, process local storage. So basically, we have a register in the process that points to the CPU environment block. The CPU environment block for each library has a pointer to the static data for the library. So if you look at this, this is an example of the code. So if you want to read a field in a non-generic class here, you have some offset for the static data of class A here. So you go and you figure out where's the static data for A live here. And then you take the field offset, add it to the base, and indirect to get to the value. So like many problems in computer science, we solve this by adding a level of indirection. The slot numbers actually need to be global across the domain. So all the processes in a domain have to have a global numbering for libraries. And the reason is that a library needs to find its static data at the same slot in every process. The slot numbering isn't known at compile time. So we made the assumption that people could upload at some point an arbitrary number of libraries. So we can't know when we deploy the system what the total number of libraries is. And we would also have to waste this valuable per process space on libraries. So the TLS storage in Windows, for example, is limited. And we'd have to waste it on libraries that are potentially not in use. So what we did is we actually have the loader number the libraries. So when you load the code, we rewrite the code, and we burn the library numbers. These are just relocations. We burn the library numbers into the code while we're loading. So the second thing you have to do is actually be able to get to code and read-only data. So in this case, again, remember, everything's in the same address space here. So what we do is, if you have an executable E, it uses a library L. So here we have library L, and we have some image E here. When we load E here, remember, we've loaded the library into physical memory here. So when we load the library here, method F occurs at some spot within the library. When we load the image E here, we just point directly at the method in the library here. So we're able to, you can just have basically a normal call instruction here to access your library code. And if you're familiar with the way things work on Windows, it's a little bit more expensive. There's a level of indirection that goes on when you do calls across libraries. The nice thing is also, when you access read-only data, you're able to take advantage of that as well. So it's just a load of a constant, or a load of an address that's known. It's just the load of an address, a normal address, to get to the read-only data. So this sounds very good. So far, it sounded pretty straightforward. I've taken libraries. I've replaced them with software mechanisms to allow software-isolated processes to use data. So we sort of replaced VM tricks with software tricks. There's a problem, though, which is that generics interact with libraries. So in this case, suppose you have some core lib which defines a generic type G, parameterized by T, and there's some class C that it also has. You might have two libraries that both instantiate G of C. So you have library A, which decides it's going to instantiate G to C, and library B, which instantiates G to C. And then you have some application that uses G of C. So the fundamental question is, well, who's going to define this instantiation? Where is this going to be defined? And what are we going to do about this? There are a couple of possible design choices for this. You could decide you're going to try to build some kind of system-level cache, where the system just has to build the instantiations as libraries come into existence. We made a different design choice. We chose to make our libraries and executables self-contained. So the implication of this is that this now means we're going to have multiple vtables floating around and multiple copies of code floating around. So when you load library A is self-contained. It gets its own instantiation. You load library B, it's self-contained. It gets its own instantiation. Now at runtime, app T has two copies of G of C floating around. The advantage of this is that we don't have any system-wide information here. When we want to unload a library, we just unload the library. There isn't somebody else who's taken a dependence on it. And this is the advantage also over having a system-wide cache is, we don't keep generics around that really are unused. When you unload things, you can unload it. And we don't have to worry about system-wide tracking of this information. But now we face the problem of living with multiple copies of a type at the same time. So we actually thought about this, and it turns out the CLR team had already thought about this as well. They had this notion of what they called potentially multiply instantiated types. I think they called it a home location. So the basic idea is that not all generic types can be multiply instantiated. So if you look at this, if library A instantiates G to a type that it itself defines, we have a home location for that type. Nobody else can instantiate that type here. So in fact, we can look at the generic types and just simply identify, is this a potentially multiply instantiated type or not? So in particular, so if you have library A and you instantiate your own type, you don't have to really worry that you're going to incur the costs. Well, I should be careful what I say here. In general, we don't have to incur the costs of potentially multiply instantiated types everywhere. There is some interaction with sharing that I'm not going to get into here. But basically, the idea is that we're going to adopt a pay-as-you-go approach. So we're going to have we're going to try to put the costs of this on potentially multiply instantiated types. So we've flagged which types are multiply instantiated, which generic types can be multiply instantiated, which ones can't. And so we're able to take advantage of this information when we're actually implementing the runtime operations. So if you, when you implement type tests in an object-oriented language, typically you use the vtables to establish type identity. So in our case, what happens is when we implement type tests, we use the vtable pointer just like you would conventionally use for object identity. If that fails, we have to fall back on an expensive structural test. So that fails, we may be seeing a generic type that is, in fact, the same type, just defined in a different compilation unit. So we actually have to go and check to make sure that all of the type arguments are identical as well. And if those type arguments are instantiations, we have to check that those are identical. There's a trick that we figured out that we can play, which is we can have a per type hash code to speed up the negative structural tests. So we can have a hash code. If the hash codes aren't different, they're definitely, or sorry, if the hash codes are different, they're definitely not the same type. If they are the same, you still have to check, in worst case, that it's the same type. And we also have to check for PMIs along some fast paths in the type test. For static fields, we solved this problem again by adding another level of indirection. So we added one level of indirection to get to static fields in general for libraries. Now we have to add a second level of indirection for getting to PMI field accesses. So the basic idea is that if you have library A and library B, and they both define G of C here, where before we would have a pointer, we'd actually be able to get directly to the field for get directly access the field for G of C, static fields of G of C. Now in this case, we've introduced an indirection. So G of C will have, for library A, we'll have a pointer to the location of static fields for G of C. And G of C instantiated in B will also have a pointer to this. And let's see, I got the arrows a little bit off here. But the general idea is the pointer points to the same space in both of them. So in this way, we can keep the identity of static fields. You can assign just once to a static field, and everybody sees it. So again, we played a game here. We added another level of indirection. And during class initialization, when we load the system up, we actually set these pointers up. So the compiler can pre-compute. The compiler chooses a winner and says, oh, I've got 3 libraries. We're going to use your instantiation and the space in your local static fields, space for your static fields set aside in the process. And we're just going to waste the space for the other static fields and the other instantiations. So with that, the key takeaway is that from these 5 things is that if you're going to use an object-oriented language for systems programming, you need to carefully go through and look at the costs. I'll show you some empirical data, some high-level empirical data that shows the importance of this. But you really need to go through and just re-examine the cost of every operation that you're doing in the system. And you need to make sure that your memory footprint, which is actually really important in systems code, is reasonable. I'm going to switch gears a bit and talk about the third approach that we've taken, which is to have a highly optimizing compiler. This is going to be a very high-level summary. I'm sure we would be happy to talk about optimizations in more depth in a future talk. So I'm going to talk a bit about the history of Bartok here. Bartok's actually the fusion of 2 optimizing compilers. So Bartok itself started off as a compiler in MSR, and the guys who used it for Singularity will remember we had no support for generics at that time. There were a lot of complaints about it, but it was hard to implement. Took me a while to solve the problem. Took the team a while to solve the problem. So, and then there was the Phoenix compiler infrastructure, which was developed by developer division. So this was a general purpose compiler infrastructure, sort of analogous. It actually predated LLVM in its goals, but the idea is to have a compiler toolkit, compiler toolbox for building compilers. Phoenix is still here. It's actually in my group. So if you're interested in using Phoenix, we're still around, and I'm happy to talk with you about using it. I think for research projects, if you're trying to do compiler research, it's actually a pretty good toolkit to use. So anyway, we can actually use Phoenix to compile both C# and C++ code. So we actually glued the 2 compilers together. I won't claim the gluing is the most elegant thing. We just glued them together, basically. So the green here represents the stuff that's from the Bartok MSR compiler, and the blue here represents Phoenix. So we read in the MSIL, we convert to high-level IR, we do high-level optimizations. I'll explain them in a second. We convert to Phoenix IR, so we do sort of object-oriented and high-level optimizations here. We also take care of all the generic stuff up in the Bartok level. Then we convert to Phoenix IR. We have interprocedural optimizations. We have inlining. We do global optimization. And then we have target-specific code generation here. So we actually have combined two optimizing compilers to do this. The compiler itself runs in 3 separate modes. And the modes really affect the assumptions that we make about the code we're compiling. We have a library mode where we just assume that everything that's public or protected is accessed outside of the compilation unit. We have an executable mode, and we actually differentiate between libraries and executables strongly in our system when compiling. In the executable mode, we assume that entry points are called externally, and we can also use information from the library compilation. So we can reuse facts about the library. And finally, we have a whole program mode, which is we assume we've got all of the code. Orthogonal to the modes, we've got profile-guided optimization. So the profile-guided optimization happens at the Phoenix level. We have not plumbed support through on the Bartok side for profile-guided optimization. So if you look at this here, we insert the probes for profile-guided instrumentation at this point, just after we convert to Phoenix IR. And then from then on out, we have profile information available. It does mean that we have to make sure that when we recompile with Bartok that we produce exactly the same IR that we started with at that point in compilation. But the profile-guided optimization and the modes are separate to each other. So in terms of optimizations, we have the catalog of optimizations here. So we have your classic interprocedural optimizations, expression simplification, expression reshaping, constant prop, copy prop, dead code elimination, unreachable code, CSE, value numbering, PRE, control flow ops, range analysis, which is sort of it's more based on abstract interpretation, trying to figure out the range or set of values that something can have. Range analysis is used for eliminating safety checks. So we can prove that something's in range. We can eliminate the bounds check. We can eliminate the null check. In some cases, we can eliminate type tests. So type test elimination is actually sort of a special case of range analysis. So we've got the full range of interprocedural, and this is, I'm sure there's stuff I've left out. We've got machine level optimization. So we've got a hierarchical tiling-based register allocator. Works actually really well. We have stack packing, instruction scheduling. We have machine idioms. We actually put a bunch of work into optimizing struct copying and struct initialization and optimizing block copying and zeroing. The block copying and zeroing is pretty well known. The struct copying was an interesting piece of work. Midori makes heavy use of structs. And for there, we have to decide, do we do a block copy or do we do a field-wise copy? And if you do a block copy, it can interfere with certain downstream optimizations. It can lead, in some cases, to suboptimal code. On the other hand, if you always do a field-wise copy, well, block copies are often more efficient on modern hardware. We also have interprocedural optimizations. So the number one thing for optimizing an object-oriented language is inlining. It's far and away the number one thing. We have an optimization that we call tree shaking. So this is what we call an instantiation and an invocation. It's what's known as an instantiation and invocation analysis. So basically, it looks at the set of types that are used in the system, a set of methods, and it prunes away anything that's not used. If you never allocate a type, in general, that means the type's not going to be used. So we're able to do that. This is actually really important when we're doing executable compilation, so that we can prune away, for example, generic code that is never needed. We do devirtualization. We do stack allocation. We do the classic interprocedural stuff that is described in literature, constant prop, bottom-up summaries. We do something we call return value optimization, where we try to avoid struct copies when you return a struct from a method. We do loop optimizations. We do loop invariant removal. We do strength reduction. We do loop unrolling. We do loop versioning. Something like loop versioning, actually, the profile information is really important for guiding that kind of thing. If you have a hot loop, you actually might want to version the loop, which is a way of splitting the loop out for tests that are in the middle of the loop that aren't always true. Sometimes they're true, sometimes they're false, but they're true or false for a large portion of the loop. And we have managed code-specific optimizations. So we do things like we specialize write barriers. We also try to optimize away write barrier insertion. If you store 0 into a field, you don't need a write barrier. We know when code can synchronize with the GC, so we avoid building GC table entries for code that can never interact with the GC. We optimize arithmetic check folding for overflow checking. And then we have, for example, the vtable merging. We try to optimize the runtime metadata. So coming back, I'm going to talk a bit about some empirical results. These are very high-level summaries of things. I mentioned before our code size ratio. This was actually the x64 build of Midori. So the 197 megabytes here, and this is total size of the executables. It includes a browser, includes shell, includes the code needed for a web server, Tetris, which of course is important, and lots of tests. So it's about 500 programs. So we have a fully functioning OS in under 200 megabytes of code. So generic sharing was one thing I mentioned. So for generic sharing, this is for an older version of the system. I didn't go and remeasure the numbers for the latest version of the system. It's a lot of work. I'll do that when we write a paper. Generic sharing over reference types gave us a 23% reduction in code size. Generic sharing over value types gave us a 10% reduction. So we're talking about 33% reduction in code size there. Sorry, in image size, actually. And shared libraries. Well, shared libraries are really the big thing, as you might guess. Trying to include megabytes and megabytes of code into your executable, it just is going to kill you in terms of code size. And for Midori, or for Singularity, we actually used whole program compilation and relied on tree shaking. Tree shaking, in our experience, gives you about a 75% reduction. So you think about 12 megabytes, even with a 75%, or 8 megabytes for one library. Even with a 75% reduction, you're still talking about huge amounts of code. So tree shaking really, from the Singularity approach, worked well enough for a research system, not good enough for production. So in this case, what we found is, and these are older versions, base was our sort of equivalent of MS Corelib, was a 50% reduction in code size. Adding the UI stack, 22% reduction in code size. Adding the testing framework, 16%. So just from these three things here, we had a cumulative, should be careful, it might have been more than, we had a cumulative reduction of 65% in code size. And that was when we had a relatively few number of libraries. I'm sure that the actual reduction in code size is even bigger today. But the basic point you should take away is if you're going to write an OS in managed code in C#, you must have shared libraries. I mean, there's no disputing it. Unless your OS is going to be extremely specialized to do exactly one thing, you must have shared libraries. And it's a great boon to the programmers, because they can use these full, rich libraries. And we don't have multiple copies of code being written. So we don't have duplicate copies of code in the OS because the code is there in the base class libraries to start with. So I'm going to switch gears. So in terms of code size, generic sharing and shared libraries are really important. I'm going to switch gears. This is actually a comparison of the code generated by Bartok on Windows. So our code, we can also produce code that runs on Windows. We have what we call bench stones, a set of micro benchmarks that were originally written for C, and then they were translated to C++ or C#, and now we use them. Actually, I'm sorry, they were originally written for like something other than C. I think it was like Fortran or something. So it was another language, and then translated to C, and then translated to C#. So anyway, these things include things like quicksort, matrix multiply, Ackermann, Drystone. So these are sort of representative of some compute-intensive things that you do, square matrix multiply, tree sorting. We have some benchmarks where the compiler got really smart and was able to basically just eliminate the benchmark. So like Fibonacci, the compiler figured out that that you were calling this function 1,000 times in a loop, but the function was the function could be hauled out of a loop. You could iterate it once and then CSE the rest of the calls. So it got to be a lot faster. So, but the basic takeaway is, we excluded those outliers because it's not really fair to include them. We're 25% faster than the JIT and NGen on x64. So for systems code, 25% is kind of a big deal. Your mileage will vary. These are micro benchmarks, but the real point is, by doing ahead of time compilation and having all these optimizations, we can generate substantially better code in our situation. And finally, this is actually a benchmark. This is actually an evaluation of just Phoenix. So I wanted to talk a bit about the quality of Phoenix itself. So this is Phoenix being used to compile C++ code. This is a Spec 2006 benchmark suite, well-known benchmark suite in the in industry for evaluating the quality of a compiler here. So we actually have compared Phoenix to a recent version of Visual Studio. It was their LKG3 release back from earlier in the year. The numbering changes a lot, but basically it's a fairly recent version of Visual Studio here. We looked at both integer and floating point performance. We looked at O2. We could have looked at Pogo or something like that, but we thought O2 is sort of the basis for everything, and the numbers are relatively similar as you increase the level and scope of compilation. And in this case, we're on par with the product C++ compiler here. So the code generator we're looking at here is a very good code generator. It can produce code that is on par with what you get from production C++ compilers. So conclusions. So this talk was about the compiler underlying Midori. There's 3 things I'd take away. I think ahead-of-time compilation of C# can work, and I think it has substantial advantages for writing an OS. We're able to show that we can deal with generics. There is a compromise, which is the libraries are brittle, but we can fully instantiate our generics at compile time. The second takeaway is that you really have to pay attention to the memory and time overhead of the system. So like I said, just in terms of code size, if you want to write an OS in this stuff, you must have shared libraries. It's just end of story. There's no disputing that. You must have shared libraries. Shared libraries are essential for Midori to be a viable OS. And if you're using generics, you're really going to want to do generic sharing. Certainly, the CLR uses generic sharing for reference types. We extended to value types. It's a significant benefit for generic code. Third, you want to avoid peanut butter. So I think for these languages, the 1% and 2% here and there really add up over time. And we're talking about a couple of percent for linked stacks, a couple of percent here. You really want to make sure that you do a good job of implementing the features, and you implement the features that people need and use. And the third takeaway is you really want a highly optimizing compiler. So you really want to make sure that you've got a compiler that is competitive with what C compilers can do. C compilers had many, many, many man-years of effort put into them. And if you don't have a highly optimizing compiler, it's going to be difficult to compete with them on just basically plain code quality. And like I said, it's primarily because the engineering and the level of optimizations that are done for them are just very good. So with that, I've finished my talk. I'm happy to take questions. I think we have about 15 minutes for questions. Thanks for listening.
Question?
Sure.
Hi. So you talked a little bit about shared libraries, the importance of shared libraries. I'm wondering how well they work in the presence of versioning. What kind of support is there built into Midori for versioning? If you have
So the answer is we don't version. We don't have support. It's an open problem to be addressed. We are working on, that DevDiv is using this format called MDIL, which is supposed to be more resilient. So in fact, we provided the early initial compiler. We provided the compiler that was actually used for Windows 8 for Red Hawk. So we actually have the capability of generating MDIL, and that would make it more resilient in terms of versioning, in terms of API changes. That's still an experiment in progress. On our side, we're going to apply MDIL to libraries. Our primary goal right now is just to reduce compile time. But once you do that, you can also do the experiment of seeing where we are when we look at release performance. But the short answer is we don't really have a versioning story here. And part of it is there's the programming model part, which I'm not really the guy to talk with about that. But at this level, we've really aimed for best performance possible. And the idea would be that if versioning is going to happen, it happens at a higher level. It happens at the application store. It happens up there, and then from the compiler perspective, we really haven't worked on versioning. We're trying to work on MDL, but our goal is actually not to achieve versioning. It's just more about build time resilience. So we have slightly subtle goals, and I'm happy to talk further with you about that.
Actually, on that point, if you had Windows Update for Midori, does that mean you need to rebuild all of your apps?
So we don't have Windows Update for Midori. Windows Update has other approaches where you don't have to necessarily download the whole library. So there's a whole application. So it would mean that in our world, you would have to recompile everything in the App Store. And so there's a reason why we're working on MDIL, and we haven't solved all of the problems yet. The holy grail is really to have all the performance I've talked about here and the resilience. But honestly, we're doing things like inlining across compilation units, so it's pretty challenging to achieve both performance and resilience. But yes, you would end up recompiling everything. The thing that we can have is multiple versions of the libraries coexisting. So it doesn't mean that you have to update everything all at once. So we do actually have the ability, or I think in our next sprint, we're going to have the ability to have libraries coexist, so 2 versions of Platform Core coexisting with each other. But then, Windows applies a lot of tricks to avoid downloading too much code later on. And so that's all stuff to be pursued in the future. Sure. OK. Yes.
C# wasn't originally designed as a systems language, and it sounds like you were relatively conservative in kind of the changes that you made or the limitations you imposed on C# to, I guess from a programmer interface sort of point of view. If you were to go through and make more wholesale changes to C# to make it more systems programming friendly, were there certain, I guess, parts of the language that you found to be, I guess, the biggest limitation in kind of having it make that transition from more of a managed language to
There's certainly stuff we've done that I didn't talk about. So the biggest thing is we actually have a variant of C# called M#. So the type system is actually quite different. So there's not just async, sync, but there's this notion of deep immutability in the type system. So I think we have made a fair number of changes to C# in what we've actually done. We have this TSE, taming side effects, type system. And so we have this notion of whether things are immutable or deeply immutable. There's been a ton of work on that, and I would actually suggest you look at some of the M# stuff. In terms of things that leap out to me, I mean, having this ability to control what's immutable is really important for concurrency. Sort of your number one lever. If you know this code isn't going to change, you can then execute stuff that accesses that data structure in parallel without worrying that you're going to corrupt the system. In terms of other things, we've mostly employed the C# attribute mechanism to specify stuff. So we do have a bunch of attributes that we added. There isn't something that really leaps out at me. C# was pretty thorough in what they've done. They've got explicit layout, which is something that Java doesn't have. And so they've got the ability to you can specify the layout. We're pretty good about matching. If you say this thing must be 13 bytes because this is some part of a network packet, we'll match that. So there isn't a lot beyond the immutability and the support. Well, and the support for concurrency. Those are really the big changes. From the getting your job done at a low level, there isn't a huge amount of stuff that I want to change.
I'd just point out that Joe Duffy gave a talk about M# this spring, and it's on ResNet as well. So if you're interested in more detail.
That is the best thing to watch.
Can developers develop against the runtime on Midori applications, or can you only do ahead of time compilation in C#?
When you say develop against the runtime?
So I mean, could you take advantage, if you wanted to develop a C# application that runs on the CLR that has reflection and dynamic types, can you do that? Or also take advantage of shared libraries and that kind of thing? Or is it only an option ahead of time?
So that's a great question. The answer is right now you can't do it. In theory, that is a direction that you could go in, which is to sort of put CLR-like functionality sitting on top of the higher parts of the system. Right now, you can't do it. We do have JITs in the system, so it's not impossible to have a JIT. We have JITs for doing graphics, and we have JITs for doing JavaScript. And we've thought about this, but we haven't actively pursued it. I would say that my vision would be you have sort of 2 levels. The core of the system needs to be this sort of tightly limited ahead-of-time compiled thing, because you just really don't want the JIT kicking off in certain places. But as you go higher up, one could envision that the main point that would be perhaps problematic is things like reflection. You'd have to limit what you can do with reflection. The idea that you can sort of reach into arbitrary parts of the system and just pull stuff out is really not good for an optimizing compiler. The more constraints you give us, the better job we can do. And if we have to keep some method around because some random person might break protection boundaries and then just call this method with some random value, that would really be a problem for us right now.
Another suggestion to avoid the peanut butter, so it's kind of like, so it looks like use a lot of like thread local storage, right? Another one approach can remove maybe 5% overhead by stealing the old like MMX registers or low intensity float point registers. You can keep.
We could do that, yes. People actually write code that makes use of SSE2 on our system, so they would be unhappy if we took the registers. What we did steal is, we just used FS and GS on Intel to get an extra register. It turns out that a lot the freezing stuff interacts really nicely with this, because if we do things right with freezing, we no longer have to worry about multiple copies floating around, multiple mutable copies of stuff floating around. So Midori has an approach where we really try to discourage people from using mutable shared statics. So we support it, because for a system at the bottom layer, you need to be able to do this.
Because also you mentioned the ABI, so you don't need to worry about some old latency code to use MSX registers.
Yes, we do control the ABI as well. So we can do all kinds. That's part of the point of this talk is, if you're a researcher and you're working in this space, you really should consider what you might want to play with here, because we have complete control over the system. We have the ABI, we have the compiler, we have the OS. So it is, I think it would be a fun playground for certain ideas, certain research ideas. In fact, one of the things I didn't mention here is that we actually use Phoenix to compile the native code for Midori as well. And so, for example, that length stack optimizations I talked about, we actually apply them to native code as well. So we're actually able to take the JavaScript, the Chakra engine, and run it inside Midori, and use the link stack technology that we were talking about here. So we have sort of total control over our environment, which is probably the one and only time I'll see this in my entire career, that we can just go and change stuff. And we've been able to do fun things. We actually revamped how we implement interfaces, for example. That's something I didn't talk about today. But it's a fun playground if you're a researcher and you have ideas that you want to try out or play with.
So I was curious, you were talking about the link stacks and having these, I guess, lighter weight processes that can kind of go. You had 200K per process. Was that where it ended, somewhere around 200K?
I think the current number, and I'm not the expert on this, I just pulled the numbers out of our nightly measurements. I think we ended up about 145K per process. And that includes setting up I think a small GC heap as well. So that is, I think, where we landed. Obviously we can keep working on making it smaller. It turns out the frozen object stuff was really actually valuable in terms of that. We actually saw a significant drop in our footprint when we did that. But I would be shocked if we went a lot lower than that, because you need some minimum amount of memory just to allocate and to exist. We have put a lot of work in Midori into reducing the process footprint size. So, if you were actually, and you can actually write small programs that stay small because most of the functionality is in the library. So, you can do Hello World in a few K. It's not big.
What are the next big challenges on this project?
What are the next big challenges on this project? Well, for Midori, I think the challenge is getting users and proving out the whole programming model, and proving this out, and proving that other people can write code on it. For us, I don't think we're done with managed code performance. So for us, the kinds of things we're working at, so one is compile time continues to remain something that we work a lot on. I think by researcher standards, you say the compile time's okay, but by production standards, compile time, we take 5 times longer than the C# compiler does to produce the MSIL for debug mode. So compile time is one practical thing that we worry about. From the research perspective, the big challenges are really about how good can we do for managed code quality. That is one challenge. So optimizing that. Another challenge is the stuff I mentioned about the fact that we're brittle with respect to our libraries. So we got plenty of interesting work to do in the system. Beyond that, there's things like cloud build, cloud compilation kinds of stuff that we can do. For Midori, though, the overall thing is proving it out. Getting users and really showing that the programming model is one that works well for people. I mentioned SpecWeb. We actually do have Midori deployed in practice. So Midori is actually deployed in the OSD data centers. If you look at Joe Duffy's talk, which is on ResNet from March, he goes into a lot more detail about what we've done with speech, where we're able to get significant improvements over the prior system. Like, I think we're about 3x lower latency and able to serve more requests at the same time. So I would point you to Joe's talk. So I think there was somebody else. Yes?
Well, for earlier benchmark, you showed that Midori was pretty competitive with Windows in terms of certain benchmarks. Was that with those programs engine on Windows, or still kind of?
So that SpecWeb thing was using however Windows actually runs, presents SpecWeb. So I would assume that, so a lot of it is first of all ASP.NET, which, so I actually don't know the answer to your question, but it's supposed to be the best configuration they've got.
Okay. And second question is, given that a lot of the modifications that you guys kind of made to C# were this framework, what kinds of, what other, can you foresee any other languages kind of being pushed into this? Because, I mean, obviously C# is kind of like probably one of the more used ones.
Yeah.
But you'd have to make a few modifications to other existing languages. How difficult would that be for certain others, would you say?
Well, I think it should be clear that like F# would probably work pretty well on this system. For other languages, it would be I think a little tough, but not impossible. But for other languages, the real thing is the concurrency model. So this notion of immutability and this notion of asynchronous computation is just fundamental to the system. So you would have to figure out for your other languages, to go way out on a limb, like something like Erlang with its computation model probably isn't too much of a stretch. I'm not sure we'd want Erlang as the language, but really it's the asynchronous programming model that would be a challenge to get into other languages. The notion, there are no threads and locks in our system, so if you have a language that starts with threads and locks, we've got a problem right there.
So speaking of getting users, I noticed you can produce code for just normal Windows out of Bartok. If I wanted to try this thing on for size and see if the programming model works for me, and I have a small pile of C# code on, let's say, a Server 2012 box, how much pain am I looking at to just take the thing out for a spin? Is that a reasonable thing to do at this point?
Well, the thing I would really point you to is there's a project over in Developer Division called Project N, and I would actually point you to them first. I don't know how well prepared they are for just random guys to try it out, but it's something that they're basically have an analogous dev-div version of the same kind of technology. Honestly, if you wanted to try it out and you're just a researcher, I think you would find that there isn't a lot of documentation, but it wouldn't be very hard to try out. What you will find is that we don't try to implement or pretend that we're the CLR on Windows. So what we found is most real code on the CLR uses like the kitchen sink. So they use reflection, and they rely on dynamic class loading and that kind of stuff. So, but if for research purposes, I'd be happy to talk with you about that. But really, honestly, if you're interested in it on a more production basis, you might consider trying to look at what they're doing for Project N over in Developer Division.
Thanks.
Okay, any more? Yes.
So the CLR's JIT has always done a really bad job at some parts of generic code. In particular, there were some idioms that were very common in generic code that required a bunch of special tweaks. Basically, we got it done on a volunteer basis for one guy when he left based on his own professional pride.
Okay.
I was wondering if you had looked at very specific idioms in generic code.
Yeah, so we did actually have to pick up the CLR idioms and implement them. They're in the compiler somewhere. I think we got most of them. I don't know if we got all of them, but we face the same. What you really need to do is avoid unnecessary boxing. There's various idioms in MSIL that can lead to boxing where you don't expect it. So we did actually look at it and pick them up. Okay, one last question.
So from the sense of the whole technique of sharing libraries, etc. So what's the story about the scaling part of it? So it seems like you have the platform perfectly set up to be run on multiple machines, a heterogeneous system with just single OS. So, I mean, yeah, what's the story around the scaling part of it?
Could you clarify the question?
So,
I'm not sure what when you say scaling, it could mean any number of things.
So, scaling in the sense how many machines how many cores in the same machine or over machines can I have this OS run on, or share, have processors share libraries over multiple machines, those kind of things.
Yeah, so for shared libraries, you clearly run them on a shared memory system. I mean, it wouldn't make any sense. Because the shared libraries are immutable, if your caching system works well on some kind of NUMA system, it should work reasonably well. You know, we are set up so that you could actually replicate the libraries. There's nothing in the system that says that you have to have exactly one copy of the library. You could actually replicate the code if you thought it was important. The libraries are pretty big, so I don't know how much you get by replicating them in DRAM. They get copied at the cache level anyway. I really can't speak to the scalability of Midori on really large core systems. I know that there are people on the team who work on that. I think we're reasonable, but it's certainly NUMA systems are an interesting OS topic that's sort of beyond my, beyond my knowledge. What I would say is that Midori has a system that's set up to scale really well on these kinds of systems because our processes have no shared memory between them. So we only rely on message passing. So certainly within a system, shared memory system with a large number of cores, say 64 cores, I mean, we're well suited in that the processes will naturally lead to good locality or appropriate locality. Clearly, when you go off the machine to another machine, I think at that point we semantically are set up, but I think the reality is that the costs are much higher when you communicate from machine to machine. So I think the programmers would need to be conscious of that kind of thing. You know, I think the idea that we're thinking about really though is more if you look at web services. If you look at web services, sort of those things are naturally parallel, and I think Midori sort of fits into that pretty well with the asynchronous nature of our programming model. So Midori itself fits in pretty well into the sort of web services approach. I mean, you have the nice feature that many problems are embarrassingly parallel.
All right. I think
Okay.
it's probably a sign that we've been here long enough.
Yes. Thank you.
So thank you, David.